How are engineers able to quantify the degree of relation between a pair of variables? Oftentimes, investigations into the correlation and mutual information of data sets can provide the answer. Correlation analysis provides a quantitative means of measuring the strength of a linear relationship between two vectors of data. In this PowerPoint presentation, I will discuss correlation, specifically population correlation coefficient, sample correlation coefficient, and correlation coefficient assumptions. Also, I will discuss what mutual information is and give a visual demonstration. The correlation coefficient, once calculated, it describes the validity of a linear fit. For two random variables x and y, the correlation coefficient ρxy is calculated as follows. The covariance of the two variables divided by the product of their standard deviations. The correlation coefficient will take on values from -1 to 1. Values of -1 and 1 indicate perfect, decreasing, and increasing linear fits, respectively. As the population correlation coefficient approaches 0 from either side, the strength of the linear fit diminishes. A modified form of the expression for the correlation coefficient describes the linearity of the data sample. For n measurements of variables x and y, the sample correlation coefficient is calculated as follows, where x over bar and y over bar are the sample averages, and s sub x and s sub y are the sample's standard deviations. This correlation coefficient will take on values from -1 to 1 corresponding to the strength of linearity. This is simpler and easier to use compared to the population correlation coefficient because it uses only well-defined statistical inputs, mean and standard deviation, rather than the complex covariance function. The correlation coefficient indicates the strength of a linear relationship between two variables with random distribution. This value alone may not be sufficient to evaluate a system where these assumptions are not valid. The four y variables have the same mean, 7.5, standard deviation, 4.12, correlation coefficient, 0.81, and regression line, y equals 3 plus 0.5 times x. However, as can be seen on the plots, the distribution of the variables is very different. The scatter plot of y1 in the top left seems to exhibit random distribution. The scatter plot of y2 in the top right does not exhibit random distribution. However, an obvious nonlinear relationship between the two variables can be observed. The scatter plot of y3 in the bottom left seems to exhibit a near-perfect linear relationship with the exception of one outlier. This outlier exerts enough influence to lower the correlation coefficient from 1 to 0.81. A Q-test should be performed to determine if a data point should be retained or rejected. The scatter plot of y4 in the bottom right shows another example when one outlier is enough to produce a high correlation coefficient, even though the relationship between the two variables is not linear. These examples indicate that the correlation coefficient alone should not be used to indicate the validity of a linear fit. Within any given process, several parameters must be selected in order to properly run the process. The relationship between variables is integral to correctly determine working values for the system. Mutual information, also referred to as transinformation, establishes the reciprocal dependency of one variable upon another. The mathematical representation for mutual information of the random variable a and b. This figure demonstrates how y provides information for x. The blue is p of x and the red is p of x and y for a specific y. In plot A, y shares mutual information with x such that, given a y1, the values of x are now narrowed down. In plot B, y still shares mutual information with x but is not as helpful. In plot C, y does not share any mutual information because the plot of p of x and y3 does not differ from p of x with y3 specified. And in plot D, given a value of y4 requires that one more question be answered or 1 degree of freedom specified to determine x. Since mutual information is always measuring a distance, the value obtained from this calculation will always be non-negative and symmetric. In both cases, the information shared between both A and B is being measured. If A and B are independent of each other, then the difference between the two would be 0. If A and B were identical, then all the information derived from obtaining variable A would supply the knowledge needed to get variable B. In summary, if an engineer were trying to determine if two random variables are linearly related, calculating correlation coefficients would be the first step in determining this. If the mean and standard deviation for both variables are known, then the population correlation coefficient should be used. If trying to determine the correlation coefficient for a given set of data, the sample correlation coefficient equation should be used. If the two variables were shown to have a high degree of correlation, the next step would be to plot the data and visibly check the linear relationship of this data. By knowing the mutual information between two variables A and B, modeling of a multivariable system can be accomplished. If two or more variables provide the same information or have similar effects on one outcome, then this can be taken into consideration while constructing a model.